Good day, students. The topic of today's discussion is interference of light and discussion of Newton's rings. So, what is Newton's rings? Newton's rings is an interference pattern. It is formed when a plano-convex lens of large radius of curvature is placed on a glass plate and coherent light is illuminated on it. ഇപ്പോൾ നമ്മളൊരു പ്ലെയിൻ ഗ്ലാസ് പ്ലേറ്റ് എടുക്കാം, അതിൻ്റെ മേലെ ഒരു പ്ലാനോ കോൺവെക്സ് ലെൻസ് വെക്കാം. നല്ല ക്യാപിറ്റൽ ആർ റേഡിയസ് ഓഫ് കർവേച്ചർ കൂടുതലുള്ള ഒരു പ്ലാനോ കോൺവെക്സ് ലെൻസ് അതിന് മേലെ വെച്ചിട്ട് ലൈറ്റിൽ കൂടെ നമ്മൾ ഇതിനെ വ്യൂ ചെയ്യുകയാണെങ്കിൽ നമുക്ക് കുറേ റിങ്സ് കാണാൻ പറ്റും. ഈ റിങ്സിനെയാണ് നമ്മൾ ന്യൂട്ടൺസ് റിങ്സ് എന്ന് വിളിക്കുന്നത്. അപ്പോൾ ഒരു പ്ലെയിൻ ഗ്ലാസ് പ്ലേറ്റ് എടുക്കാം, അതിൻ്റെ മേലെ നമ്മളൊരു പ്ലാനോ കോൺവെക്സ് ലെൻസ് വെക്കുകയാണെങ്കിൽ നമുക്കൊരു ന്യൂട്ടൺസ് റിങ്സ് എക്സ്പെരിമെൻറ്റിൻ്റെ ആ അറേഞ്ച്മെൻറ്റ് ആണ് കിട്ടുന്നത്. ഇനി ഇതിൻ്റെ മേലെ നമ്മൾ ലൈറ്റ് ഷൈൻ ചെയ്യിപ്പിക്കുമ്പോഴാണ് നമുക്ക് ഈ രണ്ട് കമ്പോണൻസിൻ്റെ ഇടയിൽ ഉള്ള സ്പേസിൽ നമുക്ക് ന്യൂട്ടൺസ് റിങ്സ് എന്ന ഇൻ്റർഫറൻസ് പാറ്റേൺ യൂസ് ചെയ്യാൻ പറ്റും. A thin circular air film of variable thickness in all directions from the point of contact of the lens at the center and the glass plate is formed. Okay, ഈ കാണുന്ന പോലെ ആ യെല്ലോ ഷെയ്ഡിലുള്ള ആ റീജിയനിലാണ് നമുക്കൊരു എയർ ഫിലിം ക്രിയേറ്റ് ചെയ്യുന്നത്. അപ്പോൾ ഈ ലെൻസും ഗ്ലാസ് പ്ലേറ്റും ടച്ച് ചെയ്യുന്ന പോയിന്റിൽ അല്ലെങ്കിൽ പോയിന്റ് ഓഫ് കോണ്ടാക്റ്റിൽ അവിടെ എയർ ഫിലിമിന്റെ തിക്നെസ് 0 ആണ്. അവിടെ നിന്ന് നമ്മൾ രണ്ട് സൈഡിലേക്ക് നീങ്ങും തോറും എയർ ഫിലിമിന്റെ തിക്നെസ് കൂടുന്നു, അല്ലേ? Now, interference fringes are a series of concentric rings with varying radius. അതായത് ഇതുപോലത്തെ ഒരു ഇന്റർഫറൻസ് പാറ്റേൺ ആണ് നമുക്ക് കാണാൻ പറ്റുന്നത്. ഇവിടെ നമുക്ക് കുറേ കോൺസെൻട്രിക് റിങ്സ് കാണാം. റിങ്സിന്റെ സെന്ററിൽ നിന്നുള്ള റേഡിയസും വ്യത്യാസപ്പെട്ടിട്ടാണ് ഇരിക്കുന്നത്. എല്ലാ റിങ്സും തമ്മിലുള്ള റേഡിയസ് ഡിഫറെൻ്റ് ആണ്, വേരിയിങ് ആണ്. അടുത്തടുത്തുള്ള രണ്ട് റിങ്സ് തമ്മിലുള്ള അകലവും വ്യത്യാസപ്പെട്ടാണ് നമുക്ക് കാണുന്നത്. So this pattern, the interference pattern of concentric rings with varying radius, is called Newton's rings. Even though it was Robert Hooke who first observed it, it was Sir Isaac Newton who first analyzed it. So that's why it is called Newton's rings. Now, Newton's rings in reflected light. Let us see what is this experimental setup. So here on a table, we have placed the glass plate, and on top of it we have a plano convex lens. So the region in between these two components, it forms the air film. Now we need to shine light upon it. For that, let us take a coherent source, a monochromatic source of light. Well, light radiates in this direction. To redirect it towards the lens combination, we place a glass plate at 45 degrees, right? Hence, light gets re-radiated upon the lens arrangements, okay? And hence, we will be able to see the Newton's rings pattern, the interference pattern. Now, to see the pattern or to measure the rings, we look through a traveling microscope. Now here a thin air film is formed between the lens and the glass plate. At the point of contact, the thickness of film is 0. Yes. When monochromatic light falls on the arrangement, interference takes place between the light reflected from the upper and lower surface of the air film. Here, interference takes place between the reflected light from this upper part of the air film and light reflected from the lower part of the air film. Interference fringes are a series of concentric rings with varying radii called Newton's rings. At the regions of constructive interference, we have bright fringes, and the conditions satisfied there are 2t is equal to odd integral multiple of half wavelength, where n is equal to 0, 1, 2, 3, etc. Here, the actual path difference is actually 2 mu t cos r, right? Since it's an air film, the refractive index mu is equal to 1. And since light is falling perpendicularly normally on this lens arrangement, angle of incidence is very small, hence R will also be very small. Okay. Thus, cos R tends to be 1. Thus, we get the path difference to be 2T. Now, at the regions of destructive interference, dark fringes are seen, and the condition satisfied there is 2T is equal to integral multiple of wavelength, where n has any integral value 0, 1, 2, 3, etc. Now, at the center, the thickness T is 0, and hence the condition for destructive interference is satisfied. Hence, at the center, a dark spot is observed. See, when T is equal to 0, which of these conditions can be satisfied? When T is equal to 0 here, even if N is equal to 0, the right hand side will have a value, right? It will be lambda by 2. So this equation is not satisfied on both sides. Whereas here, when N is equal to 0, your right hand side is 0, and at T is equal to 0, left hand side is 0. Hence, the condition for destructive interference is satisfied at the point of contact. Thus, the central spot is dark. Now, the Newton's rings is this pattern, and we need to understand the nature of the fringes. The central dark spot is observed when we view in reflected light. Understand this. We are looking upon this arrangement and we are looking into the reflected light in this direction. Okay. We are observing the Newton's rings in reflected light. Okay. Now, here Newton's rings are circular fringes. Okay, there is no doubt in that. The radius of the dark fringes is proportional to square root of the natural number. So we shall calculate it here. That is, radius of the nth fringe Rn is equal to square root of nr lambda. Here r is the radius of curvature of the lens. It's a constant. Lambda is the wavelength of the source light. That is also a constant. It does not vary. Hence, the variable here is root n. The rings are not evenly spaced. That is, as n increases, the rings get closer. And each fringe is of equal thickness. So each of the circular fringe, if we observe, it has equal thickness, right? This is because in that circular ring, it actually shows the locus of all points in the air film having the same path difference. Okay. Now, hence, each fringe will be of equal thickness. So using Newton's rings experiment, how can we measure the source length? For that, let us do some calculations. Now assume the parameters given here. We have a glass plate here upon which a plano-convex lens is formed, and thus an air film will be formed between them. Let the center of curvature of the lens be point M, and the distance from M to the surface of the lens be MO. Okay. Here it makes an intersection at N, and let this point be P and this point be Q. So at PQ, we will be observing the nth fringe, and the distance from the point of contact to the nth fringe will be Rn. So if R is the radius of curvature of the lens, we have MO is equal to MP is equal to capital R, right? Then thickness of the film PQ is defined as small t. Here by Pythagoras theorem, I can write Pm square is equal to Pn square plus Mn square, right? Here Pn is shown in red just because we have taken into consideration the nth fringe. Okay. Now, instead of Pm, I can replace capital R. Instead of Pn, I can replace small rn. And instead of Mn, I am going to replace capital R minus T. Okay, so doing the substitutions and expanding this equation, I get R square is equal to Rn square plus capital R square minus 2 capital RT plus t square. That is, Rn square is equal to 2RT minus t square. Here, the radius of curvature is large, so it will be much larger than the thickness of the air film. Hence, we can consider 2RT to be very much larger than the term t square, and hence neglect t square. We get Rn square is equal to 2RT. Now, the condition for the dark fringe in the air film is 2T is equal to n lambda. So let us substitute for 2T here. We get Rn square is equal to nr lambda. That is, the radius of the nth dark fringe is obtained as Rn is equal to square root of nr lambda. Likewise, we can do the calculations for the bright fringes, and we will get the radius of the nth bright fringe as Rn prime is equal to square root of odd integral multiple of half wavelength into capital R. Now, the diameter of the nth dark ring will be twice its radius, right? So, dn is equal to 2Rn. That is, dn is equal to 2 times square root of nr lambda. The diameter of the n plus 1th dark ring will be dn plus 1 is equal to 2 into square root of n plus 1 r lambda. Right. And the diameter of the n plus kth dark ring will be dn plus k is equal to 2 square root of n plus k r lambda. Now let us take dn plus k square minus dn square, and that will give 4n plus k r lambda minus 4nr lambda. That is equal to dn plus k square minus dn square is equal to 4k lambda r. Thus, the wavelength of the light source lambda can be written as dn plus k square minus dn square divided by 4kr. You may pause the video to write down this derivation. Now, while doing the experiment, first of all, once we view the Newton's rings through the traveling microscope, we bring the cross wire to the center of this circular rings. We should take importance to bring it to the center, because unless it is at the center, we might be measuring the chord of the circle. We need to measure the diameter of the circle. So make sure that you are at the center of the circular fringes. If we have seen the center of the circular fringes and place the cross wire there, now move to any of the sides, right or left, to the 24th fringe. Okay, so here let me move to the left side. Okay, now I am counting the fringes on the left side, and I have reached the 24th fringe. Okay, I have reached the 24th fringe, and then I come back to the 22nd fringe. See, I'll be moving my screw along one direction to reach the 24th fringe. Okay, and then I'll reverse it to come back to the 22nd fringe. I have done this to remove the backlash error, because in all the calculations I'll then be moving only in one direction. See, first I have taken the reading at the 22nd fringe as XL22. Then again I move towards the right and take the reading at XL20, that is the reading of the 20th ring on the left side. Right. So I'll be continuously moving towards the right till the end of the experiment. Next, I'll take the reading of the 18th fringe on the left side. Then I'll take the reading on the 16th fringe on the left side. Then I'll take the reading of the 14th fringe on the left side. Then I'll take the reading of the 12th ring on the left side. Then 10th ring on the left side. 8th ring on the left side. 6th ring, 4th ring, 2nd ring. Then I'll cross the center and take the reading of the second ring on the right side. Okay, then fourth ring on the right side, sixth ring on the right side, eighth ring, 10th ring, 12th ring, 14th ring, 16th ring, 18th ring, 20th ring, and 22nd ring. Okay, after we've taken all these readings, okay, then we can measure the diameter. Now here I have taken the n values as even numbers 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay, this is just an example. Okay, it can vary in different methods. Now for n is equal to 2, that is for the second ring, the diameter of the second ring will be XL2 minus XR2. Okay, so now let us assume K to be 10, then the diameter of the n plus kth ring, that is the diameter of the 2 plus 10th ring, will be the diameter of the 12th ring, right? So dn plus k square minus dn square is equal to d12 square minus d2 square. Okay. Thus, we calculate the dn plus k square minus dn square for all n values. Here I've just taken the first value 2, right? Now next we take 4 and then calculate d14 square minus d4 square. Next we take d16 square minus d6 square, likewise. And calculate all the values for dn plus k square minus dn square and take its average. Using Boy's method, we are going to calculate the radius of curvature of the lens capital R, that is equal to FD divided by F minus D. Here, F is calculated using the plane mirror method and D is measured using the Boy's method. In the plane mirror method, we have a source light covered with wire gauze and place the lens and a plane mirror placed behind it in front of the source light. We are arranging it such that we get an image near the source itself. Okay. Now we adjust this lens and plane mirror combination such that the image is clear and it is identical to the source. And thus the distance between the source and the lens gives the value of small f. Now repeat this experiment by replacing the plane mirror with a black paper. And again, we adjust this combination, the lens and the black paper combination, so as to get a reflection of the source light near it itself. And once you get it, you measure the distance from the source to the lens again as small d. And using the values of f and d, you can calculate the radius of curvature capital R. Hence, source wavelength can be calculated for k is equal to 10 as lambda is equal to dn plus k square minus dn square divided by 4 kr, where k is equal to 10. Now this was for an air film, right? Now if we have a source of known wavelength, we can use this arrangement to measure the refractive index of a liquid. Now for that, what we do is dn plus k square minus dn square is calculated for the air film. Now we place a few drops of that liquid onto the glass plate and then place the plano-convex lens on top of it. Hence, a liquid film is produced by placing 1 or 2 drops of the liquid between the lens and the glass plate. Okay, and then again we measure the diameters, that is dn plus k prime square minus dn prime square is calculated for the liquid film. And the refractive index of the film mu is given as the dn plus k square minus dn square divided by dn plus k prime square minus dn prime square. Now, Newton's rings can also be observed in transmitted light. So here, let us see what are the differences in its arrangement. If you can notice, the source light is placed under this Newton's rings arrangement. Okay, so light will pass through it and hence we will be able to see the transmitted light. When monochromatic light falls on the arrangement, interference takes place between the light transmitted through the upper and lower surface of the air film. Again, interference fringes are seen, which are a series of concentric rings with varying radii. And at the regions of constructive interference, we get bright fringes, and the conditions satisfied there are 2t is equal to m lambda. Here, there is a change. Okay. This is because there is no additional path difference due to phase change. So the conditions here in transmitted light is 2t is equal to m lambda for constructive interference, and at regions of destructive interference, dark fringes are seen, and the condition satisfied is 2t is equal to odd integral multiple of half wavelength. Here I have used the integer m so as not to confuse with the integer used earlier. At the center, t is equal to 0 and the condition for constructive interference is satisfied. Hence, in transmitted light, we can observe Newton's rings with a central bright spot. Now, the radius for the bright ring is Rm is equal to square root of mr lambda, and radius of the dark ring Rm prime is given as square root of odd integral multiple of half wavelength into capital R. Now, one of the important applications of Newton's rings is we can use it to test the optical flatness of different lenses of glass plates. Okay, so here, if you look into this image, we can see the Newton's rings on the surface of the air film. Okay, the air film is seen, it is actually in between the glass plate and the lens. Okay, so if the rings are exactly circular in nature, we can say that the lens has a perfect curvature, or the glass plate placed beneath is exactly plane. Okay, if there is any irregularity in the circular nature, we can say that there is a default at that point or there is a crack at that point. Okay, so we can test the optical flatness of surfaces using Newton's rings. Well, with that, we have come to the end of today's discussion. Hope you will learn well. Thank you.